Okay, in 9.2, we're going to take a look at what are called multistage experiments. And if I'm being really, really transparent, I will tell you this is the section I think the students dislike the most of this chapter for sure, maybe the whole semester. What it really is, though, is it's a structured way of creating a diagram to help you with a multiple-stepped problem, okay? We're creating a diagram to help us to do something that has more than one step. So that diagram is actually called a tree diagram. A tree diagram is a sample space model where each outcome is designated by a separate branch. I promise we'll create them. Let's just get our vocab done first. When we're doing one-stage experiments, that's what we did in 9.1. It's all one-stage experiments, okay? One thing happened. We rolled the die one time. We pull out a hat from a hat. You haven't done the homework for it, but you'll pull out one number from a hat. You're going to select one person to go on that cruise. It's all about doing things one time. The experiment's over after one step, after one set of branches, and so we don't really need to draw a tree diagram. The situation's just simple enough, it's not necessary. But what happens in this section is that we're going to encounter two-stage experiments or more. And that means the experiment actually has two sets of branches. So we roll the die two times. We draw two numbers out of the hat. We send two people on the cruise. Whatever it is, we're doing it with 2 or 3 or 4, etc. Okay, you're doing something over and over again. And we did talk about the idea of doing something over and over again a little bit in the last section. We talked about large numbers, right? The law of large numbers, Bernoulli's equation, and how we're able to sort of approximate over time what happens if we have a whole lot of them. But we didn't do a problem where we had a whole lot of them that we did. That's the difference, okay? There's a multiplication rule for tree diagrams. As we look at a tree diagram, which we will soon, you can actually find the outcome of whatever the branch is by multiplying the probabilities along the branch. You just multiply outcomes together and you get the outcome at the end as the percentage or the probability. And here's my note. I expect to see tree diagrams or something similar, and I'll show you something similar kind of things in certain circumstances. And the reason is because this is what you would expect of a student at the level of junior high and below to do if they were doing something similar. Are you going to do ones more complicated than they are? Yes, of course you are. You're in college, okay? Yes, you are. But even with the simple ones that you would ask a student to do when they're exploring probability, which they do in 7th grade curriculum, by the way, that's usually the standard place where it's first encountered is 6th or 7th grade, but 7th grade most of the time. They would be drawing a diagram to help them make those decisions. They wouldn't just be number crunching, which some of you at this point would be like, why wouldn't we just do it this way? Because your thinking is more advanced than the 12-year-old you're teaching, right? Of course it is. That's why we're going to do it this way. Okay. Independent events are events where the occurrence of one event has no influence on the outcomes of the second event. For example, whether it rains today has absolutely no bearing over whether it rains on April 1st. They're too far apart. They're independent events. If I select one student from this class and invite you to come to lunch with me, and I select another student from my Calc 3 class, those are independent events because whether you're selected in this class has no bearing over whether the person was selected in the Calc 3 class. That said, not all events are independent events. Whether it rains tomorrow does have some bearing over whether it rained today, right? There's an effect to it. Right? If I select one person from this class to go to lunch with me and then I select a second person, well, who I selected first does in fact affect who is selected second because you're in a group that's the same group of people I'm selecting from. So there's some context to it that decides and helps you decide whether or not your events are independent. But the key determining factor is, do they have any effect on one another? And if they don't, they're independent. If you have independent events, that the probability of both of them happening is the product of their individual probabilities, right? So the probability that it rains today times the probability that it rains on April 1st multiplied together would be the probability that both those things happen. And we could do the same thing with selecting people to go to lunch. What we're going to do, though, is we're going to send people to Hawaii. That sounds pretty good, doesn't it? It does. So we're going to take an executive committee. The committee consists of 10 members. Right? So this would be like my idea of taking people in this classroom, but there's 10 of them. Of the 10 of them, there happen to be 4 women and 6 men. 3 of them are getting an all-expense-paid trip to Hawaii. That's exciting, yeah? Okay, so let us take a look at what we're deciding from. I want to flip my screen, and you're feel free to flip your paper, but we're going to come back and use the space at the bottom of page 1, if you've printed them off, to draw our diagram. But drawing our diagram is going to be dependent on what kind of questions we're asked. And I want you to see where our questions are leading us so that you can see why we're drawing the diagram the way that we are, okay? Question A says, what is the probability that all 3 selected are women? And question B says, what is the probability that at least one selected is a man? So what this is telling you is that there's categories that we're deciding between, and the categories are men and women. Right? They're not the individual 10 people. I'm not asking whether Jill gets to go or not. Right? I'm asking whether a woman gets to go or not. Those are different kinds of questions, agreed? Okay, it matters what the question's asking as to how you're going to draw your diagram. So when I come back over here to draw my diagram, there are going to be 2 branches from my original statement. So I'm going to draw like a node right there. And I'm going to draw 2 branches, branch 1, branch 2. And the distinguishing factor between these branches is as to whether or not we have a man or a woman's name that's drawn out of the hat, because all my questions had to do with whether they were male or female, right? That's what they had to do with. So that's the only thing that I need to have represented on my picture. So imagine that I put all of their names in the hat, completely unbiased. It's completely randomized. They've just got names and slips of paper, and I reach in and I pick one out. Okay? What is the probability that a man's name is drawn from the hat? 6 out of 10. There are 6 names in there that belong to men, and there are 10 names in there total. So then, what is the probability that a woman's name is drawn out of the hat? It is 4 out of 10. Does everybody understand the first set of branches? And I hope as you're looking at this, you understand why, if we only sent one person to Hawaii, there's no need to draw this picture. What good does it do me to draw the picture? It's really just the answer 6 out of 10 or 4 out of 10, and I can just look at the problem and tell you that, right? The problem is we're not just sending one person to Hawaii, we're sending more than one, and specifically here we're sending 3. It's probably important for me to also note that these are not independent events. Right? Once I pick one person's name out and send them, or put them in the stack of people who are going to Hawaii, that person's name is no longer in the basket. So there's no longer 10 people's name in the basket. It's been changed. It's been affected. These are not independent draws out of the hat. Right? Now imagine the problem was a little bit different, and instead of sending people to Hawaii, we're just giving people money. And we say, once I give the person money, their name goes back in the hat. Okay, so I draw out a name. This person gets $100. I give them $100, but their name goes back into the hat. Well, then we're back at the beginning. It's a fresh draw. There's an independent event because the situation was exactly like it was to start with. Still have 10 people's names in the hat. But that's not what I have here. So what happens is after I draw that person's name out, I'm going to draw another set of branches coming from each one of the men's and women's. And as you're drawing these, people are always like, how do I fit it all in? If you make your branches longer, you have more space to work. When you make your branches really short, you're going to feel like you're running out of space. Okay, so if you stretch out your diagram, you'll have better space to work in. Okay, but when I draw the second time, I'm still looking at whether or not I've drawn out a man or a woman's name. So I'm going to the ending part of each of these branches is still man or woman. But what happens is that each of these branches are potentially different numbers, and they're also going to be different than the 6 out of 10 and 4 out of 10 to start with, because the basket has different numbers of names in them. In fact, how many names are in my basket now? Only 9. So the denominator for every single one of these is going to be 9, because there's only 9 names to draw from. Now, the numerator is going to depend on what has happened before because these events are not independent. It depends on what happened before. So if I'm along my top branch, the man's name was chosen, correct? If a man's name is chosen, how many men's names are still in the basket? Only 5. So I only have a 5 out of 9 chance of drawing out the man's name. How many women's names are still in the basket? 4. So there's a 4 out of 9 chance of drawing a woman's name. But if I come along the bottom branch where the woman's name was drawn, a woman's name was drawn first, how many men's names are still in the basket? 6. And how many women's names are in the basket? 3. Now let me make a comment. Some of you are going to promptly forget, but write it down so that at least if you look back in your notes, you have it later. As you look at these sets of branches, and by that I mean these pair that go together, these pair that go together, these pair to go together, what I want you to see is they always add to 1. Okay, so if you're in the middle of a problem and you're finding your branches don't add to 1, you've got an error somewhere. Maybe you set it up completely wrong. Maybe you just counted something wrong. But every pair of branches, right, they have to add up to 1 because that's 100%. It's all the options represented. Does that make sense? Okay, I'm going to take away my yellow on here since I've got more to draw. Because I'm not just sending 2 people to Hawaii, I'm sending 3 people to Hawaii. So I need another set of branches off of each of these at the end. And remember, I did warn you to draw them long. I think this is the biggest one we're going to do today. There's another one that's equal in size that we'll do next time in this lesson. But what's the ending result of each one of the branches? Man or woman, right? Still M's and W's. So I'm just going to fill them in. I have MW, 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 MW. And at this point, how many names are in my basket? 8. So the denominator for all of my fractions is going to be 8. The numerator will depend on where we've come from. So if I come along the first 2 branches like this, 2 men's names have been drawn, right? Okay, how many men are left in the basket? 4. How many women are left in the basket? 4. If I come along the first branch that leads to the second like this, a man's name and a woman's name have been drawn, right? Okay. How many men are still left in the basket? 5. And how many women? 3. Now, catch this. This branch, where it goes woman, man, is the same thing. The orders were done differently, but I still drew 1 man's name and 1 woman's name. So these 2 branches that I'm about to fill in right here, are going to be the same as up here. Because I already have the same people's names, or at least by gender, drawn out. So if I've drawn out a man and a woman's name, how many men's names are left? 5. And how many women? 3. All right, last branch down here at the bottom, or last set of branches. I've had 2 women's names drawn out. Okay. How many men are left in the drawing? There's still 6 of them. And how many women? 2. Okay, when you do a tree diagram, you will put the probabilities along every branch. Now, some tree diagrams will have all the same probabilities everywhere, and we'll see some examples of them, okay? Like every single branch is going to say 1/2 or something like that, okay? And that's fine. There are contexts where that happens. But the context here is that everything keeps shifting and changing because the drawing pool of names keeps changing from draw to draw. Is everybody okay with that? If we can't draw this picture, we can't answer the questions. So this is the picture that we're going to refer back to as we look at the questions posed. Question number 1. What is the probability that all 3 selected are women? So looking along my branches, where does this occur? Okay, where is it, Avery? Okay, the last 2 8s right here, right? In particular, more descriptively, it occurs along this very last branch down here, agreed? This very last branch down here is the only place where all 3 selected are women, agreed? And over here, it said that we have a multiplication rule for tree diagrams. I can find the likelihood of that one branch by multiplying the 3 probabilities along its branches together. So I can multiply 4/10 and 3/9 and 2/8. So that's what we're going to do. We're going to multiply 4/10 times 3/9 times 2/8. Now, if this is one that we can reduce and simplify and clean things up, we will. If you want to multiply everything out and then simplify the fraction, that's fine too. But unless there's a good reason to change it into decimal form, we're not going to do that. This one cleans up pretty nicely, actually. So you might notice some of these canceling out pretty quick. 3 and 9 both reduce to 1 and 3. They both divide by 3. 4 and 10 both divide by 2 to give me 2 and 5. 2 and 8 both divided by 2 to give me 1 and 4. And if you don't notice anything else, that's fine. There is one more that you could reduce if you happen to notice along the diagonals, the 2 and the 4. I'm not going to mess with those at the moment because I don't think that you will always see them, and I want to show you what happens if you don't. So if you get to this point after you've reduced your individual fractions, this would give me a 2 on top and a 60 on bottom, I think. Yeah. If at this point they're still able to be simplified, right, we will. And this will give me a 1 out of 30. There is only a 1 out of 30 chance that the 3 people going to the trip are all women. Yes, ma'am.
So how do we know if you want us to answer in a fraction or in decimal?
So what typically happens is that decimals are given in the problem when it's being described, like you're told probabilities. For example, let me show you the next one. The one that I'm thinking of is this one. Do you see how they show up in decimal form? Mm-hmm. We're going to give this an answer in decimal form.
So would it be counted wrong if we answered like this one?
So that's a good question. On this one, the answer is yes, and here's the reason why. If you put 1 over 30 in and you find out what that decimal is, it's going to be a repeating decimal. And we're not going to answer our answers with repeating decimals and repeating decimal form for probabilities unless you're specifically told, turn this into decimal form. And occasionally you might be with context, but a lot of times you're not. So unless you're told to turn it into something, we won't. We'll leave this in fractional form. Good questions. All right, the next question's a little more subtle. The last one's a very direct question. All 3 women. But question B says, at least 1 man. What does that phrase, at least 1 man, mean? What could happen that satisfies that criteria? 1 man. What else could it mean? 2 men and 3 men. Does everybody understand that phrase, at least 1? We're going to be dealing with that phrase at least and at most a little bit in this section. At least 1 means it could be 1 man, 2 men, 3 men, which really just means it's not what? It's not no men or all women. Agreed? Why does it matter? Let me show you why it matters. If you go back to this diagram and you want to find all the ways that you can have at least 1 man, let's just start highlighting them. Well, here's at least 1 man, and here's at least 1, and here's 1, and here's 1. And here's 1, and here's 1, and here's 1. All of those branches have at least 1 man on them. And if you wanted to find this probability directly, you'd have to multiply all 7 of those out and then add them together. Doable? Sure. Worth your time? Probably not. And the reason it's not is because we had a theorem last time that talked about complements. And it said something like this. The probability of A complement is 1 minus the probability of A. This was one version of it. There were several versions. What this is actually telling you is if you want to find the likelihood that something's not going to happen, right, that we're not going to get all women going to the conference, what you can actually do is you can do 1 minus the likelihood that that very thing is exactly what happens, which is what we found in part A. We did that. It's 1 over 30. So instead of multiplying along 7 sets of branches and then adding them all together, we can take what we did in part A and we can subtract. Whether you thought to or not, this will give you a way to get a common denominator. And then 30 minus 1 would give me 29 out of 30. 29 out of 30 chance that at least one of our gentlemen is going on this trip. Is that all right? Okay. The next one I'm going to show you is actually one where there's another option in terms of showing work. If you don't like the tree diagram approach, we're going to do more tree diagrams later, but I want to show you another option in terms of work. We have a box. It contains 5 slips of paper. The 5 slips of paper are numbered 4, 6, 7, 8, and 9. Okay, pretty good so far. A player reaches into the box and draws out 2 slips of paper and adds them together. If the sum is even, the player wins. If the sum is odd, the player loses. Okay, can you picture doing this activity? Okay, you could picture doing this. It's very descriptive. It's very helpful. So when we reach in and we draw out our number, we have 5 different choices, correct? So one way to do this would be to draw a tree diagram with 5 branches off of it, right? The branches would be 4, 6, 7, 8, and 9. And there's nothing wrong with doing that. The problem is then that off of each of those 5 branches, you'd have to draw 4 more on each of the 5 branches. And when you're done with all of it, you'd have 20 branches. It'd be a very big diagram. Agree? Yeah. So there's another way that we could do this too that condenses the writing load at least down a little bit. So let's take a look at what we could do. We could draw out a 4. And we could draw out, actually I won't write it with plus right now, we'll go back and put those in a minute. I could draw out a 4 and a 6. I could also draw out a 4 and a what? 7. Or a 4 and a 8. Or a 4 and a 9. And this is the only way that I can draw things out where I draw out a 4. If I flip any of these around, I don't get a different draw of 2 numbers. I get a different order maybe that I drew them out, but I don't actually get a different outcome because I'm just going to add them together in a minute anyway, right? So this is all my outcomes that have the 4 in them. So now we're going to move on to saying, okay, well, I didn't draw a 4. If I drew out a 6, not going to rewrite 6, 4. I already listed that. What could I list? 6 and 7, or 6 and 8, or 6 and 9. Okay, I don't need to list any more 6s. I've explored all those possibilities. Now I'm going to look at what happens if I draw a 7. I don't need to list 7 and 4 and 7 and 6. I already did that. So 7 and 8 or 7 and 9. Okay, no more 7s. What else is left? 8 and 9. And I think I'm done, right? Okay, so I'd like for you to go back now, and we're going to sort of play the game out and look at what these outcomes are in terms of addition. So if I add these together, what do I get? 10. Add these together, I get 11. Add 4 and 8, I get 12. 4 and 9, 13. 6 and 7, 13. 6 and 8, 14. 6 and 9. I'm going to give myself a little more space. 6, 9, 15, good. 7 and 8. That one's 15. 7 and 9. That one's my 16. And then I have 8 and 9. 17. So these are the different summed outcomes that I could pull out. So check it out. It wants to know the probability that the player wins. Okay? What does it mean to win this game? Yeah, the sum is even. So we can go through all the red numbers that I've listed and find the ones that are even. The 10 is, the 12 is, 14, and the 16. These are my even numbers, right? So how many outcomes are even? Did you count them? There were 4 outcomes that were even, unless I missed one. Did I miss any? I think I got them all. How many outcomes were there total? 10, yeah. And this will reduce to what? 2 out of 5. We counted. Just counted these up. There's 1, 2, 3. 10 of them, yeah. Okay. Okay, so Jabora, back to the question you asked before. What if I turned this into a decimal? You could do it here. The reason you could do it here is because 2 out of 5 is a terminating decimal. It's just 0.5, or 0.4, excuse me. So it would be totally fine if you took this in decimal form because it stops. Okay?
It would also be correct if it's just 2 out of 5.
Exactly, yeah. Okay, let's change the rules of the game, though, slightly. Does the probability change if the two numbers are multiplied? So no longer are we going to add, we're going to multiply them. And if so, to what does it change? So let's go through, and we're going to change these, and we're going to multiply them instead. But actually, I don't really want to multiply them together. I just want us to highlight the ones that we know are going to get to be even when we're done. And if you aren't sure how to make that decision, we'll see if we can explore that idea. I'm going to take out my red. Okay. If I multiply 4 times 6, is it going to be even? Yes. 4 times 7? Yes. 4 times 8? Yes. 4 times 9? Yes. Why can I do that without actually multiplying them? And I don't mean like I memorized multiplication tables and I actually multiplied them. We don't have to multiply to do this. Do you know how you know those are going to all be even? It's because the 4 is even. Yeah. If you're multiplying by an even number, you're going to get an even result. So if that's what we're thinking then, is 6 times 7 even? Yep. 6 times 8? Yep. 6 times 9? Yes. 7 times 8? Yes. 7 times 9? No, that's our first one that's a no, right? And then how about 8 times 9? That one's a yes. So is this probability going to be different? Well, yeah. I got a lot more that I highlighted in blue. In fact, how many of them are highlighted in blue? 9 out of how many? 10. So there are 9 out of 10 that actually would have this work for us. Okay, any questions on that? Okay, so we're going to push pause on this lesson right here today.